Okay, we continue our study of rings. In particular, we explore some more integer-like properties of rings. Here's a definition. Let D be an integral domain and let A and B be elements of D, and suppose D is not 0. So 0 means 0 element of this integral domain. So it doesn't necessarily mean that 0 as a number. Okay. Then we say B is a divisor of A. So this is definition. If and only if there exists an element C in D such that A is equal to B times C. Okay, so just like integers, we define a divisor in this way. Next, let's review the notion of a unit. Okay, we have been using this notion repeatedly already, and we say an element. Okay, let's say R is a ring. We say U, an element of R, is a unit. So what this means is the following. There exists some element, another element in this ring such that UV is equal to VU is equal to 1. Okay, this one is, again, it's not necessarily a number, but it is the identity element of this ring. Okay, identity element in this case means so for any element in the ring, the identity element behaves like 1 times A is equal to A times 1 is equal to A. So such an element is called the identity element, or multiplicative identity of the ring. Okay, so this is just a review of the notion of unit. Now, using this, we define the following notion. So we say again, suppose D is an integral domain. And we say A is, so A and B are elements of D. A is an associate of B. So by this we mean there exists a unit U in D such that A is equal to BU. So B times some unit is equal to A. Okay, so in this case we say A is an associate of B, but this also implies, since U is a unit, there exists some element V in D such that U V is equal to 1. 1 is the identity. So if you multiply V from the right to the both sides of this, we have A V is equal to BU V, which is equal to B times 1, which is equal to B. So therefore, B is equal to AV. So what this means is that if A is an associate of B, that implies B is also an associate of A. So in other words, the relation of associate being an associate is symmetric. And next we would like to introduce one lemma, but before that, let us review the notion of this, where R is a ring and A is an element of the ring. Okay, so what this means is the following. So this is a set where elements are expressed as the product between x and a, and x is any element of R of the ring. Okay, we have seen that this is an ideal. This not just ideal, it should be a left ideal, unless R is a commutative ring. Okay, then let's introduce this lemma. Okay, again, D is an integral domain. And let A and B be elements of D, and then then B divides. Well, B is a divisor. Divides A if and only if dA is a subset of dB. So let's prove this, and for convenience, when we say B divides A, we write B divides A just like for integers. Okay, so here's the proof. Since this is if and only if statement, we need to prove both directions. So first, let's try only if part. So suppose B divides A. Then there exists some element C such that A is equal to BC. Or since we are assuming this is an integral domain, so it's a commutative ring, so this is equal to CB. Okay, let's write like this. And therefore, dA, so this ideal is equal to dCB, but this is a subset of dB. So only if part is proved. And conversely, so if part. So suppose we have dA is a subset of dB. Okay, and in particular, since D is an integral domain, we have the identity element in D. So A is 1 times D, 1 times A, which is an element of dA. But since this is a subset of dB, so this means A is an element of dB. Therefore, there exists some element C in D such that A is equal to C times B. Therefore, B divides A, and we are done. Okay, next lemma. Again, D is an integral domain. And that also A and B are elements of D. Then the following four statements are equivalent. So dA is equal to dB is equivalent to A divides B and B divides A. And 3, A and B are associates. And 4, A is equal to BU for some unit U. Okay, and we can immediately see that 3 and 4 are equivalent because this is just a definition of associates, right? So A and B are associates if there exists some unit relating them like this. And 1 and 2 are equivalent from the previous lemma. So if from the previous lemma, if B divides A, then dA is a subset of dB. And in addition, if A divides B, then uh, sorry, then if so if A B divides A, then this is equivalent to D. A is a subset of dB, and if A divides B, then this is equivalent to dB is a subset of dA. So if these two holds at the same time, then dA and dB should be equal. So these are equivalent. So what's left to show is this equivalence. Okay, so let's show this. Okay, so let's prove if 2 is true, then 3 is true. Okay, so suppose A divides B and B divides A. Then there exists some elements C and D in the integral domain such that B, let's say, A is equal to BC and B is equal to AD. Okay, then let's see what we do want to see. So they're associates. Okay, so A is equal to BC, but if we substitute B with AD, then we have AD C. But since D is an integral domain, D is an integral domain, there are no proper divisors of 0. We can cancel A. So from this, we can cancel A to have DC is equal to 1. Okay, so this means C and D are units. Therefore, that means since we can write like this, A and B are related in this way. So therefore, that means by definition, therefore A and B are associates. And we are done. Let's see a few examples. Consider m and n in the set of integers. So these are associates. If and only if m is equal to plus minus n. Why? So according to the previous lemma, A and B are associates if and only if A divides B, B divides A. So in the case of integers, m divides n and n divides m indicates this is the only possibility. And in the integer ring, the only units are plus minus 1, positive 1 or negative 1, because only these numbers, integers, are invertible within integers. And next example, consider f, which is a field. And based on that, consider the set of polynomials of x over f. Okay, in this case, the units of this polynomial ring are non-zero elements of F. So that means, so elements of F are also polynomials, but polynomials without any powers of x. So it's a constant polynomial. They are constant polynomials. So that means if f of x and g of x are polynomials over f, then they are associate if and only if they are related like this. C times g of x for some c in f, and c is not equal to 0. 0 is again is the zero element of the field f. So it may not be a number, but it's the additional additive identity element of the field f. Okay, so f of x and g of x are associate if there exists some non-zero element of f such that they are expressed in this way. Okay, so of course, since f is non-zero, we can divide both sides by 0. So therefore, g of x can be expressed as 1 of, maybe we should not use 1 over c, but c inverse f of x. And c inverse is, of course, an element of f. Because by definition, non-zero element or every non-zero element of a field can be inverted. So we can always find C inverse within F.